Okay, so last class we had discussed the normal mode of a helical antenna. Okay, so this class we will continue with the second mode or the axial mode. For axial mode, the diameter of the dimensions of the helix, they are comparable to the wavelength. Remember, for the normal mode, the dimensions were much smaller compared to the wavelength. But for axial mode, dimensions of the helix are comparable to the wavelength. Okay. In general, the range is 3 by 4, that is C by lambda naught by 4 by 3. Ideally, C equal to lambda naught. Where C equal to pi d is the circumference of the helix. Is it okay? Is it okay? So, for the axial mode, the first thing to be noted is that the dimensions of the helix are now comparable to the wavelength. Okay. And the pitch angle, it usually rises from 12 degree to 14 degree. Right. The radiation pattern for this helix antenna is end fire, and it is somewhat similar to the next antenna we will discuss today. Okay. Sorry, it's difficult to draw. The 3D radiation pattern is approximately like this, but you should refer to Balanis for a better picture. Difficult to draw like this. The helix is like this. The helix is actually here. Okay. So this is the radiation pattern of the helical antenna in the axial mode. Please compare to the broadside pattern of the same helical antenna when it is operated at the normal mode. Right? The impedance, the input impedance of a helical antenna in the normal mode is usually pure resistance, whose value is R is almost equal to 140 by C lambda naught. Okay, the half power beam width is 52, almost equal to 52 lambda naught to the power 3 by 2 square root of C by ns. Okay, the first null beam width is given by 115 lambda naught to the power 3 by 2 C into square root of ns. Directivity is 15n C square S by lambda naught cube. Do you remember what is the axial ratio of a polarization? This is just formulas. There is no need, just you can remember the formulas, one or two, the directivity again. No need to do the derivations, way above the scope of this lecture. Do you know what is axial ratio when it comes? What is axial ratio? E theta by E phi. Yes. In a specific case, yes. In a specific case, yes. In general case, for a circular polarization, there are two components, right? Remember, for circular or for elliptical polarization, there are two components. Okay, what I told E theta E phi, that is correct for the spherical coordinates. For basic Cartesian, it is Ex and Ey. Take okay. So the axial ratio is simply the ratio of this Ex and Ey. And of course, there are two components. There will be a 90-degree phase difference. Okay. So for circular polarization, what will be the axial ratio? One exactly, right? For a circular polarization, acceleration ratio will be 1. Axial ratio in this mode is given by 2n plus 1 by 2n. So how to achieve circular polarization for a in the axial mode? How to achieve circular polarization? We have discussed last class how to achieve circular polarization in the helix antenna in the normal mode. So how to achieve circular polarization in the helix antenna in the axial mode? The axial mode should be close to 1, right? Exactly, very good. All of you agree? If the number of turns are much more than 1, then we can achieve circular polarization. Okay. Actually, if you think that not much more, even n equal to 3 2 or 4, we can take that it is circular. Okay, very close to 1. So questions which can come is like, in what mode of helical antenna we can have circular polarization? Option A is axial mode, option B is normal mode, option C is both, option D is neither. Okay, so these type of questions you can expect in your exam. Okay, so I think that should be enough for, or what type of a pattern we have, and we can see broadside, end fire, both depending on mode or neither, or this type of questions, you understand? Not no tough derivation will be asked, just basic, like, or you need to I will tell you to calculate the radiation resistance of our in the axial mode. So you just need to use this formula and get the answer. Okay, so no complicated formulas or no complicated derivations will be asked in the exam. Just formulas like this, just add multiplication and division. Okay, so that's, I think that should be enough for helical antenna. But I request all of you, if please go through the lectures by Professor Girish Kumar on the YouTube. Okay, he discusses this in very great detail, and that will give you a far better understanding on the helix. Okay, so please go through the lectures. So any questions regarding helical antennas? Whatever discussed yesterday and today. Any questions regarding the helical antenna? Yeah, this formula. Use this formula. The input impedance is a resistance. Okay, for helical antenna, the reactance part is very small. For the resistance part, just use this formula. You will calculate. This is in ohms, of course. Okay. The next antenna which we are going to discuss today is an Yagi-Uda array. Okay. So this was invented in Tohoku University of Japan around 1926, and the inventors were Uda, S. Uda, who was the student, a researcher, I don't remember correctly exactly, and his professor H. Yagi. Okay, so they invented this antenna. The most striking feature of this antenna is the presence of parasitic elements. What is a parasitic elements? Parasitic elements, they are not energized separately. What is a parasite? Can anyone tell me what is a parasite? What is a parasite? Feeds off its host, right? Exactly. So the parasite cannot uh, take have or hunt or make its own food, so it feeds off the host. Exactly like that, the parasitic elements, they do not have their own feed. Okay, they work with the induced EMF due to the feeding element. Okay, the parasitic elements, they stay near the feeding element. So when some current is fed on that feeding element, or some current is induced due to incoming wave, some other, it induces it by coupling, some other voltages or currents are induced in the parasitic elements as well. At those, at the fields created by those induced voltages currents, they combine with the fields of the main element to give some patterns. Okay, which is a lot different from the actual feeding element. Okay, is it okay? So the parasitic elements, they do not have any feed of their own. How does an Yagi-Uda antenna look? The blue element is the feeding element. Okay, the blue one, this is the driver or the feed element. Usually it is a dipole if we want an impedance of close to 75 ohms, or a folded dipole if we desire an impedance of 300 ohms. Okay, this we have seen that the folded dipole, the impedance is 4 times of a dipole. Okay, the red elements, they are called the director. And the dipole, the feed element's length is almost lambda by 2 at resonant length lambda by 2. The length of the director, sorry, very sorry, this is a reflector. Sorry. This is a reflector, not the director. This is called the LR, that is greater than LF. Okay, not much, slightly greater. Okay, and the green elements, they are called the directors. LD is less than lambda by 2. Okay, so this is a basic structure. There is one feed element, which is a dipole or a folded dipole, depending on what type of resistance you want from the antenna. There are usually one reflector. Okay, there can be more, no problem, but that will not help much. The reflector length is slightly larger than the feed element, and there are multiple directors. Okay, and the length of the directors are slightly smaller than the feed element. Any questions so far? The reflectors and directors, they are not excited. Okay, or neither any voltage is taken from it, any voltage is taken from it. The exciting element or the connected element is only the feed element, which is the dipole or the folded element. Any other questions from anyone so far? This separation, this is between 0.3 lambda to 0.4 lambda. Okay, and the diameter of the elements is around 0.05 lambda, or the radius is 0.025 lambda. Okay, fine, all of you agree? Okay, great. Now see, what we had discussed, that if the antenna is at the resonant length, its impedance is what? A resistor or a capacitor resistance, or a R plus Jx or R minus Jx. The 0.05 lambda, 0.05 times lambda, not 0.05 as 0.05 lambda, or lambda by 20, whatever you want to be. Okay, acha, yes, so we had discussed that suppose we have a dipole, okay, at the resonant length. So this is say 0.45 lambda to 0.49 lambda. So how will the impedance look from the source point of view? Will it be a resistance? Will it be a reactance? Will it be an inductive reactance? Will it be a capacitive reactance? Or how it should look? How it should look? this impedance, what is Z in? Option is R. Option A is R. Option B is R plus Jx. Option C is R minus Jx. Option D is Jx. Option E is minus Jx. So what should be the impedance or Z in from that source at the resonant length? What is the input impedance of a dipole at its resonant length? What happens to the antenna at the resonant length? What happens to the antenna near its resonant length? R minus Jx. Okay, anybody else? Actually, at resonance length, the impedance is a pure resistance. Okay, there could be some X, but that is very small. If we increase the length past its resonant length, then the impedance becomes inductive, and if the length is slightly smaller than the resonant length, then it is capacitive, like R minus Jx. Okay, so this reflector will be inductive, and this didactors will be capacitive. Okay, the reflector will have a inductive impedance, and the capacitors will have, and the didactors will have capacitive impedance. Agreed? Okay. Do you agree? Is it okay? Right. Now what happens in an inductor? What is the voltage current relation in the inductor? The phase relation of voltage and current? What is the phase relation of voltage and currents in an inductor? Voltage leads or current leads for an inductor? Yes, right. Voltage leads the current, right? And what about the capacitors? For a capacitor, the current leads. Okay. So think in this way. This is an inductor where the current is lagging. This is a resistor where the current and voltage are in on the same phase, and these are capacitors where the current is leading, okay, the voltage. So there is a, think it this way, there is a lead, there is a phase change, there is a phase lead. If this phase angle is 0, this phase angle will be alpha 1, this will be alpha 2, this will be alpha 3, and this is alpha 4. So can we write this? Can we write this? In some Yagi-Uda antennas, the subsequent directors are even smaller in size. Okay. In some, it is not. Can we write this? That as we move on from the reflector to the feed element or the driven element to the directors, there is a gradual change of phase, and the currents in each element, they are leading the previous elements in phase. Is it okay? Now tell me, what type of a beam we expect in such a situation? What is the pattern of antenna beam we expect? From your knowledge of antenna arrays, what will be the, it will be a broadside pattern or an end fire pattern? From your understanding, what should it like be? The pattern will be broadside or end fire? Why broadside? What is the condition for getting a broadside pattern? We discussed when we discussed arrays. What is the basic condition of getting a broadside pattern? Think what we have discussed, what we have seen in the antenna arrays discussion, and then answer. What is the condition of getting a broadside beam pattern, and what is the condition of getting an end fire beam pattern? Is the black bar comparable to array here? What do you mean by black bar? Yes, broadside, the backside is perpendicular axis. That is absolutely correct. I agree with you. But how to get that pattern? And okay, black bar is that. No. Black bar is not an element. Black bar is a structure on which the elements are connected. Let me show you. Black bar is not an element. Okay, black bar is neither a radiating element nor a parasitic element. Black bar is a structure. Okay, let me show it to you. Then wait. Yeah. See here. This is the reflector. This is a driven element, which is the usually a folded dipole. Okay, because we want the 300 ohm resistance to be connected with the, and these are the directors. Okay, this is your black bar. What we were saying. This is not an element. Okay, an actual picture. Maybe this one. See, reflector, the driven element, and the directors. See here, directors are gradually smaller in size. Why? Because we want to make it more and more capacitive, so that as we move from here to here, the currents in the elements, they lead more and more in phase. Is it okay? Is it clear? The black bar is not an element. The black bar is this one. Is a structure on which the antenna rests. Is it clear, Niloy? From this photo, is it clear? Wow. Anybody from Bhopal? This antenna, you can buy it actually. What is the price? 2,500 rupees. Okay, very good. Read what is written. If you don't understand anything, tell me. You don't have to buy the antenna, just read what is given. Very, very interesting things are written here. Can you read it? Read. Okay, do not add physical inductance. Do not add physical inductance. That is not. Interestingly, they have given the input 50 ohms. There should be. Note the gain of this antenna, 13 dBi. In absolute terms, what does it mean? The frequency range, it is quite broad. I think it covers all the GSM frequency, right? It fully covers the GSM band. The bandwidth is quite broad. This is not for TV, okay? The original analog TV, the frequency range is much less. So this is not for TV. This I think is for the GSM. GSM band is covers fully. Gain is 13 dBi. What does it mean? Gain is 13 dBi. What does it mean? What does gain of 13 dBi mean in the specs? That is your job as an engineer to understand, right? Given the specs, you have to understand. What does a gain of 13 dBi mean? Anyone? What does a gain of 13 dBi mean? Anybody? And this is a typical value of gain we expect from an Yagi antenna. What does a gain of 13 dBi mean? What is antenna gain? We discussed, right? Anyone want to try? What does a gain of 13 dBi mean? Tell me fast. Yes, dB over isotropic, right? So 13 dBi is how much approximately? Without calculation, can you tell me? How much is 13 dBi in a linear scale? How much is 13 dBi in linear scale? Very good, 20. Yes. How did you calculate? Not 13 log, Ritika. 13 equal to 10 log A. Okay. If you solve this equation, then A is approximately 20. Yes, yes. But Rakesh, thing is that 13 dB I told you, because if you see 13 dB, right, it is very close to 20. You can say it without calculator. What you said is the exact 19.5 the exact value. Okay, VSWR less than 1.5. What does this mean? 5 minutes remaining. What does this mean? VSWR is less than 1.5. What is VSWR? We discussed this in the lab classes. What is VSWR? Voltage standing wave ratio. So what does this mean, that VSWR less than 1.5? If the antenna is very good, well balanced, very well matched, the VSWR should be what? How much? If I match my antenna perfectly, then what should the... Okay, we'll discuss this at the next session. 5 minutes. Better take the attendance.